Hello guys, welcome back to my YouTube channel. So today we are going to solve day 15 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 2179. Count good triplets in an array. Okay, so you are given two zero indexed arrays nums1 and nums2 of length n. Alright, same length, both of which are permutations of 0, 1, 2 and minus 1. Okay, so here n is 4, right? So you see that in both these arrays we have numbers from 0 to n minus 1, 0 to 3. Okay, 0, 1, 2, 3. Okay, so only these numbers are there in both these arrays. Okay, now what is this good triplet? A good triplet is a set of three distinct values which are present in increasing order by position both in nums1 and nums2. Okay, in other words, if we consider position 1v as the index of the value v in the nums1 and position 2v as the index of a value v in nums2. Okay, then a good triplet will be a set xyz where xyz it should be from 0 to n minus 1 such that position of element x, okay, it should be less than position of element y, position of element z. Okay, same way position of element 2, okay, x, and here position of element y and position of element z. Okay, so see here what actually it is saying here. Here if you see, we have to form the set like x y z. Okay, so here from this array you can form like this 2, you can pick first 2, then you can pick a 0, then you can pick 1. Okay, then also you can do one thing, you can pick 2 first, then you can pick 1, and then you can pick 3. Okay, this is also one valid option. Then if you start from 0, then you can pick here 0, 1 and 3. Okay, so this is also one valid. Okay, and also you can also pick this 2, 0 and 3. Okay, 2, 0 and 3 you can also pick from this, right? So here if you see in all these the index, okay, so x y z, okay, so these are nothing but, let's suppose, index. Okay, so here see the index of this 2 is smaller than this index, okay, than this index, right? So here this y index is smaller than this z, right? So position of the elements, okay, so position of the elements of 1x, it should be less than position of element of 1y and position of element of 1z. Okay, this is clear. But from here nums2, if you see what are the different you can form, you can form 0, 1, 2, this is what you can form, you can form 0, 1, 3 you can form, then you can form 0, 2, 3 also, right? And then you can form 1, 2, 3. So now in these two, tell me which is same. Okay, so here out of here from these four and from these four, you see only this 0, 1 and 3 is same. Okay, in both places 0, 1 and 3. So see here, now if I draw this, so 0, 1 and 3 here, so here also 0, 1 and 3. Okay, so this is what we need to find, right? There are four triplets x, y, z such that position of 1x less than position of 1y less than position of 1z. They are this. Out of these triplets, only the triplet 0, 1, 3 satisfies this position of 2x less than position of 2y less than position of 2z. Hence, there is only one good triplet. Okay, that's it, right? And same way this example 2, here if you see, so here the four good triplets are 4, 0, 3. Here's 4, 0 and 3. Okay, here also this 4 first coming, then 0 coming, then 3. Okay, then this 4, 0, 2, 4, 0, 2. Here also if you see 4, 0 and 2. Okay, correct order. Then here 4, 1, 3, 4, 1 and 3. Here if you see 4, 1 and 3. Okay, this is done. Then here last one 4, 1, 2, 4, 1 and 2. Here also 4, 1 and 2. Okay, so only these four, right? So 4 is my output. Okay, and these are the constant size. Okay, nums1 dot length, nums2 length, it's equal to n, and n is ranging from 10 to the power 5. Okay, from 3 to 10 to the 5. Okay, so nums1 and nums2 are the permutations of this. Okay, all right, so now this is clear how we are getting the output. Okay, so position of element x, y and z. Okay, so they should satisfy this condition. Okay, and same way this one. Okay, so both are matching where we have to return that. All right, so in this question I'm going to solve this problem using Fenwick tree. Okay, so actually this topic itself requires one separate video, okay, in which I can explain things like what is this Fenwick tree and with diagram explanation, how we fill the values, how what is the functionality of this. Okay, so this topic actually requires one separate video, so but let's try a little bit, okay, in this video as well. All right, so what is this Fenwick tree? Okay, so Fenwick tree or binary index tree is a data structure used to calculate the range queries along with updating the elements of the array, okay, such that each query or update takes logarithmic time complexity. It is used to calculate the prefix sums or running total of values up to an index. Okay, so let's say you have elements like this 2, 1, 4, 5, 6. Okay, so now you have this is at 0 index, 1 index, 2 index, okay, 3 index, 4 index. I'm not going to cover much, okay, only few things I will cover here. Okay, otherwise this video is going to become very lengthy. Okay, so I will try to make one separate video on this topic. Okay, so here if I ask you to calculate the sum in this range 0 index to 3 index, so what you are going to do, you are going to iterate over all the elements one by one. Okay, so here this is the first thing that you are going to do, brute force. Okay, all right, so this is one thing that you are going to do. Then after that, I may ask you to update the element at index 2 with the value, let's say 6. Okay, I can say something like that. So then you have to update this. Okay, so but if there are so many queries, okay, here here you have to calculate the prefix sum in this range, then update, then prefix sum, then update the prefix sum. Okay, update, there are so many queries. Okay, so what is the one approach that you can do first? So it's not okay na, right? But you are going to again and again do of and time complexity 0 to 3 you calculate, then here I'm asking 0 to 6 you have to calculate, then here I'm asking you to calculate 4 to 6 index. So this is not right now, you are again and again going to run it off and times. Okay, so this is going to give time complexity like number of queries you have and the length of this. So q into n is going to be your time complexity. So this is bad. Okay, if q and n very large, let's suppose it is 10 to the power 5, it is 10 to the power 5, so you are going to get a time limit exceed error. Okay, so what is this Fenwick tree is going to do? This is a data structure which is used to calculate the range queries along with updating the elements of the array such that each query or update takes only logarithmic time complexity. Okay, so if you calculate this, see this, if you calculate the prefix sum, okay, if you think little bit smart, so you are going to do what you are going to do, you are going to calculate the prefix sum here. Okay, so until here prefix sum is 2, 2 plus 1 3, 2 plus 1 plus 4 is 7. Okay, 7 plus 5 12, 12 plus 6 18. Okay, so now if I ask you to calculate the sum from prefix sum, okay, you have to calculate from 2 to 4, then what you are going to do, you are going to simply say me that until here total sum, okay, until here total sum, you are going to say that it is 18. So in 18 you are going to subtract r1. Okay, so you are going to subtract until here. Okay, so this sum until here is nothing but 3. Okay, so 18 minus 3 you are going to say 15. So 6, if you see here 6 plus 5 11, 11 plus 4 15. Yeah, you are right. Okay, so now you are a little bit smart here, you calculate the prefix sum. Okay, but now so many prefix sum ranges updates. Okay, now if I say that I don't want to use 4 here, please update this to 6. Okay, so here you have incremented with the 2, so here this will be incremented to 9, then this will be incremented to 14. Okay, this will be incremented to 20, right? Right, okay, so here 2 3 6 9 9 5 14 20. Okay, so again if you do update, then again everything is updating again and again. So that is the problem, right? So we don't want this prefix sum as well. Okay, we have to use something else. Okay, this prefix sum we are doing, but we are doing in of qn. Okay, qn, queries and n. Okay, so of and we are doing again. Okay, update is becoming costly, right? If you calculate the prefix sum and later on update is coming, then you have to update this prefix sum. Okay, so that is the issue, right? So that problem is solved by this Fenwick guy. Okay, so why to use this Fenwick tree? Whenever we have the range queries along with updating the elements of the array such that the number of range queries are comparable to the number of updates in the array. Okay, then we can perform both of these operations in logarithmic time using Fenwick trees. Let's say we are given an array of size n and q queries, okay, of two types. Okay, so here queries of two types. Okay, so type 1 is where we are given two integers l and r. Okay, so this is a range. Okay, and we need to calculate the sum of elements in the range l to r. Okay, and type 2 where we are given two integers I and x, where we need to update the element at index I to x. Okay, so this is what, right? And why use a Fenwick tree? Okay, so same thing. Okay, so here update a single element in O of log n time, then query the prefix sum of elements from index 0 to I in O of log n time. It is much faster than recomputing sums from scratch every time and simpler than segment tree. Okay, so now this topic also requires one separate video. Okay, what is segment tree? Okay, so I will try to make a separate video for this Fenwick tree and segment tree. Okay, because both are pending, right? When you only need these operations. Okay, so here intuition behind this Fenwick tree: imagine you have an array and you want to frequently update a single element and frequently ask for the sum of first I elements, and natively we are going to use like this operation update in of one time prefix. Okay, with the Fenwick tree you can do both in of log n time. Okay, so structure: the Fenwick tree is usually implemented as a one based array. We add 1 to all the indexes. For an array of size n, the Fenwick tree has size n plus 1. Each node in the tree represents a range of elements, and the binary representation of the index helps us jump efficiently. Okay, so now here let's see, understand it with some example. Okay, so I will not take much time here. Okay, so let's suppose this is array given to us, right? Okay, so here if you see carefully how many number of different elements we have. uh, this is at 0 index. Okay, 0 1 2 3 4 5 6 7 8 9 10 11. Okay, 11. So 11 is the size, right? 11 is the size of this. 12 is the size. Okay, we are starting from 0 now. Okay, so 1 2 3 4 5 6 7 8 9 10 11 12. Okay, 12 is the size. Okay, so here 0 is dummy. Okay, so I told you in structure that Fenwick tree is usually implemented as a one based array. Okay, so here if you see, here I'm writing 0, then here I'm writing 1 2 4, I'm writing here, I'm writing 8. Okay, 3 I'm writing here, 5 I'm writing here, 6 I'm writing here, 7 I'm writing here, 9 I'm writing here, 10 I'm writing here, 11 I'm writing here, 12 I'm writing here. Why? What is this now? Okay, so that's why I'm saying that this topic requires one separate video. Okay, so let me just give you a little bit hint. Okay, so okay, so every number, okay, every number you can represent that particular number in form of 2, right? So 1 you are going to represent it like this, 2 power 0. Okay, 2 you are going to represent like this, 2 power 1. Okay, 3 you are going to represent like this, 2 1 plus 2 power 0. 4 you are going to represent like this, 2 power 2, you can represent it like this. 5 you are going to represent like this, okay, 2 power 2 plus 2 power 0. 6 you are going to represent like this, 2 power 2 plus 2 power 1. Okay, and 7 you are going to represent like this. Okay, in maths, 2 power 2, here 2 power 2 4, here 2 power 1 plus 2 power 0. Okay, this is how you are going to represent. Okay, so now see here, 1 2 power 0. Okay, so 1 we are representing with 2 power 0. Okay, so here 2 power 0. Okay, so 1 is connected with just 0. Okay, then here this 2 we are representing it with 2 power 1. Okay, so here this 3 I'm connecting with this. Okay, and then if you see this 4, this 4 I am connected with this. Okay, and this 6, okay, here let's write it 1 2 and 4, and this, sorry, not 6, this is 8. Okay, then 8 we are connecting. Okay, but here why? Okay, so here see one thing, see one thing. Okay, one in this how I'm writing it in binary form, I'm going to write it in binary form like this. Okay, 2 I'm going to write it in binary form like this. Okay, then 4 is okay, 4 is connected now. 4 I can write it like this, 0 1 0 0 in binary form, and 8 is connected. Okay, 8 I can write 8 like this, 1 0 0. Okay, so now here what you need to do, let me move a little bit to this. Okay, so now here this is the set bit. Okay, from the right side. Okay, so rightmost, this is a set bit, this is a set bit. Okay, from the right side I'm checking first set bit. Okay, this is a set bit, first set bit. Okay, this is a first set bit, that is I'm checking from this side. Okay, first. Okay, so what you need to do, just off this bit. Okay, just change it to 0. Okay, so then you are going to get 0 0 0. Here also you are going to get 0 0 0. Here also you are going to get 0 0 0. Here also you are going to get 0 0 0. So all these are 0. Okay, so connected with 0. Okay, now let's take this example of 3. Why 3 is connected with this 2? Okay, so if you take the 3 example, so 3 how I'm going to write in a binary form, 3 I'm going to write like this, 0 0 1 1, right? Right, now this is a leftmost. Okay, this is the rightmost, right? So you have to change it to 0. So you are going to get 0 0 1 0. So what is this? This is nothing but 2. Okay, so that is why this 3 is connected with 2, right? Clear? Okay, this 3 is connected with 2. Okay, now if you take this example 7, why 7 is connected with this 6? Okay, so 7 you are going to write it in binary form like this, how 1 2 4, okay, 4 5 6 7. Okay, this is how you're going to write. Okay, so this is the rightmost, so you 0 1 1 and here 0. So what is this value? This is nothing but 6, so that is why this is connected with this. Okay, so now this is done. Okay, all right, so now this is done. Okay, now here if you see here if you see, okay, now next thing you can ask, why we are writing, how we are getting this this array, fan array 1 to n. Okay, so we know this 1 2 4 8 this how this green colored ones are coming. Okay, how these green colored ones are connected. Okay, so here see everything is in a logarithmic this tree height and logarithmic n. Okay, so now in this I will store the prefix sum. Okay, so in this fan array, so now how I'm going to fill this 2 3. Okay, so here this is 1. Okay, so here you have to fill from 0 to 1. Okay, so that simply means there is only one. Okay, there is only one element. Okay, 0 0 is a dummy, right? There is nothing here, so only 1. So you have to fill all the elements until this 1. Okay, done. Then here you are getting 3. That simply means from starting from this 0. Okay, so starting from this 0 to 0. Okay, so here you can write 0 comma 0. Okay, because if you're going to refer this now, so you can write 0 comma 0 for your reference. Okay, 0 comma 0, so only one element. So here until 2 now, so 0 comma 1 you can write. So here 0 comma 1, so you are going to write 3. Okay, so here 0 and 4 ending, so you can write 0 to 3. So 0 to 3 elements 0 1 2 3 3 4 5 6 7. Okay, 7, right? Here you can write 0 to 7. Okay, so this is the sum of 0 to 7. Okay, then After that this is 1 here. Okay, so this is 1 at 2. Okay, so here what is this, starting from 2 2 3. Okay, so here you can write 2 only, right? 2 here you can write, and until 2 only, 2 to 2. Okay, so what is 2 element? So 1 only. Okay, so here you are going to write 4 and 5, so 4 to 4 you can write. Okay, and here you are going to write 4 to 5. Okay, and here 8 to 8 you can write, right? Here a starting from 8, and you have to give one last index. Okay, 8 to 9, and here 8 and 8 to 11. Okay, so 8 to 11, this is a prefix sum, 30. So 0 1 2 3 4 5 6 7 8, 8 to 11, 8 9 10 11. Okay, so here calculate now. 8 plus 6 14, 14 plus 7 21, 21 9 30. Okay, that is why 30. Okay, so here this is nothing but what is this, 6 okay, this is 10 now, so 10, and here you have to give 10. Okay, and this is a prefix sum from 6 to 6. Okay, so this is how, so this is a sum. Okay, so now later on, if I ask you to give me the sum until 8. Okay, this is a better side. Okay, this side I can ask you to give me the sum until 12. Okay, so until 12. Okay, until 12 give me the sum. Okay, 0 to 12, 0 to 12. Okay, so how you are going to do that? So 0 12. Okay, 0 to 11, our input array is from index 0 to 11. 0 to 11. Okay, so I ask you to give the sum from 0 to 11. Okay, not to 12. 12 is the size. Okay, why I'm taking 12? Because here this is one base index now, so this is dummy. Okay, so here in 1 I'm writing 0 0 only. 2 I'm writing 0 to 1. Okay, so if I ask this, okay, so what you are going to do, you have to just simply check what is the sum here. At this you are going to say 30. Okay, okay, then what is this parent? This parent is this, so here add this 21. So this is going to be a total sum, that is nothing but 61. Okay, now why 61 is correct, so I can prove that. So this 30 is sum from 8 to 11 range, and this is the sum 21 is the sum from 0 to 7 range. So you are adding the elements from 0 to 11, all the elements, that's it. Okay, so now this is done. Okay, so now this is done. Okay, so how we are adding this? Okay, now this is clear. We have spent so much time here, I don't want to spend this much time. Okay, for this, because I want to make a separate video for this. All right, so now let's see this part first. Okay, so all right, so here what we are doing updating the value at the particular index to achieve the updation at a. Okay, so this is first part. Okay, calculating the prefix sum and the range. Now to achieve the updation at a particular index, we implement the method update Fenwick. Note that updating the value at a particular index doesn't create any impact on the input array, it only creates the impact on the fan array that we are creating here, fan array. Okay, so this method updates the value at index y with the value u. Okay, assign the value y plus 1 to the current index, repeat steps a and b until the current. Okay, so just go over these steps. Okay, and this is one formula. Okay, to update, this is the formula that I'm going to use in my code. Okay, this is one formula that I'm going to use in my code, and this is the formula that I'm going, this is one more formula that I'm going to use in my code. Okay, so how to update get array sum. Okay, so here idx minus idx and minus idx. Okay, this is the formula. Okay, so here go to the parent of that particular index. The parent can be reached by truncating the last set bit from the current index. Okay, how to reach the parent? So I already told you now here how we are reaching the parent. So what you need to do, like this 3. Okay, 3 is nothing but you are going to write like this 0 1 1. Okay, you have to just make it okay, so let's say here let me try this formula. So 3. Okay, 3 idx is 3. Okay, so here 3 and minus 3 is nothing but it is going to be a minus 3. How we represent? So first 3 we are going to represent it like this 0 0 1 1, and what is the complement of 3? You have to update, you have to just opposite all the bits. Okay, 1 1 0 0, then this is nothing but 1 2 4 8, this is nothing but 12. Okay, this is nothing but 12 now. Okay, all right, now in this you have to add 1, so you are going to get 13. Okay, now 13 you are going to represent like this 1 2 4 8 13, you are going to represent 1 1, and here 1. Okay, 1 1 0 1. Okay, so minus 3 is nothing but this 1 1 0 1. Okay, so we just how to calculate the value of minus 3? Take the value of 3, take its complement. Okay, flip every bit 1 1 0 0, and just what is the output 12, in that add 1 13, and 13 how we represent like this. Okay, then and operation among them. So if you do and, okay, that's what I thought, that why we are getting wrong output. Okay, so we are getting here what we are getting here, just 1. Okay, so now 3 minus 1, if you are going to get what 3 is the, okay, so here index is nothing but 3, and here you are going to get 1. Okay, and 3 minus 1 you are going to get 2. Okay, so 2 is the output, right? So here for this 3 you see that parent is 2. Okay, so this is what we need to find now. 3 parents is 2. Okay, so this is right now, this is 3, 3's parent is 2, green color. Okay, so we were doing some mistake here, okay, because of this. All right, so now this is done. So this is the formula to reach the parent. Okay, same way if we update, so for update also there is one formula that is given here. One second, this side. Okay, so this is a formula which is given to update. Okay, so in the update, okay, add the value v to the this, okay, FAANG index, go to the next element of FAANG index by setting the last bit of the current index. One can find the next element, that is idx plus and minus idx. Okay, so same formula you have to implement. Okay, so here let's think like that. Okay, so let's suppose if you are making some changes here, okay, it is also starting from 0 to 1. Okay, then you have to make the same thing here also, right? Because it is also starting from this 0 to 3. Okay, so this is the reason. Okay, we are going to update the value at the particular index. Okay, so just try this formula, okay, and you will get to know. Okay, so index of parent j can be obtained using the formula this. Okay, so we are going to find the index of the parent j. Okay, all right, so now let's come back to our question. Okay, now here see, this is the input given to us. So first what you need to do, this is nums2 na. So here 4 is at 0 index. Okay, this 1 is at 1 index, this 0 is at 2 index, this 2 is at 3 index, this 3 is at 4 index. So step 1 is done. Okay, mapping positions of elements in nums2. Okay, now after that we have to this is my nums1. Okay, 40132. Okay, 40132. Okay, so 40132. Okay, so now what here I am going to do here, uh, see here, from here I can simply say now. Okay, so this 4 in nums1, this is at 0. Okay, okay, here in nums2 this 4 is at 0. Okay, and here also it is at 0 now. So just write the position. This 4, it is at 0. Okay, it should be at 0. Okay, from nums2, if I check this in nums2, it should be at 0. Okay, this 0, it should be at this index. Okay, 1 or 2, sorry. Okay, then this 1, this should be at index 1 as per nums2. Okay, this 3, it should be at index 4 as per nums2. This 2, this should be at index 3 as per nums2. Okay, so 0 2 1 4 3. So this is what I'm writing, 0 2 1 4 3. Okay, mapping the position of elements of nums1 in nums2. So you are clear now. 4, this should be at 0 as per nums2. 0, this should be at nums of this should be at 2 as of nums2. Okay, this one, this should be at first index as per nums2. This 3 should be at index 4 as per nums2. Okay, this is what you need to calculate. Okay, so now here you have to find the elements in such like this x should be less than y, this y should be less than j. Okay, these elements, okay, x element, y element, z element. Okay, this should be the case, right? So here in this, if you see, if you form this, so you can form this 0 1 3, you can form 0 what else you can form, 0 1 4 you can form, right? And here you can also form 1 not 1, you can form here this is done, right? 0 0 1 and 3. Okay, I want such like this as x. Okay, this is y. Okay, this is z position. Okay, so I want in such a way that x should be less than y should be less than j. Okay, so here you can form this 0 1 3, and okay, this is also right now 0 to 4 and 0 to 3. Okay, so I think that's it. Okay, so here in all these cases x is less than y is less than j. Okay, so position of element x, okay, it should be less than position of element of y, less than position of element z. Okay, so total 4 we can form. 4 is my output now here, if you see. Okay, so here if you see, that is right now, that is right. Okay, so 0 1 and 3. Okay, this is what we can form, right? 0 1 and 4 we can form, right? Okay, all right, as per this 0 2 1 4 3. Okay, these are the 4 we can form. Okay, so okay, so step 2 done. Okay, until step 2 we are done. Step 1 is done, step 2 we done. We know how we are getting this 0 2 1 4 3. Okay, now we have to count the good triplets. Okay, so now we need to count good triplets x y z such that position of 1x should be less than position of 1y, position of 1z. Okay, index positions in nums1. Okay, this is index position in nums1, and position 2x less than position of 2y, less than position of 2z, index position in nums2. We will do this step by step for each element in mapped positions. Okay, so these are nothing but my mapped positions, 0 2 1 4 3. Okay, so now see here. Okay, this is accepted. Okay, I thought of giving the dry run with this. Okay, but let's see this one. Okay, let's see this one. Okay, this is a much detailed one. Okay, mapped positions. Okay, at num1 I. Okay, so nums1 of I, index in nums2. Okay, is 02143. Okay, so this is the indexing, right? 02143 that we have calculated in step 2. Okay, now this is done. All right, so now initially I am at here 02143. Okay, I am at here. So now here I'm at here now. Just before the left of this, tell me the number of indexes which are smaller than this. Okay, tell me the number of indexes which are smaller than this. 0. You are going to say left count 0. Okay, the number of indexes in the right side of this which are greater than this. Okay, so let's suppose this is my y. Okay, now I want to find x and z. So z in this range. So number of elements which are greater than this y. So 1, 2, 3, 4. You are going to say 4. Okay, so 0 and 4. So see now here, triplets from this index is 0 into 4. Okay, so here you see in this there is nothing 0. We don't use 0 anywhere in the mid. Okay, so there are no triplets possible, right? Okay, now after that same thing here. Now I will treat this as my y. Okay, just go over these things side by side what I'm doing. So 0 I've used one time now, so here I will just increment the bit count of this 0 to 1. Okay, 0 we have calculated. Okay, 0 we have already calculated. Okay, so here this is for 0 2 1 4 3. Okay, so now I'm at here. Okay, so now I'm at here. Okay, so now in the left side number of indexes x which are smaller than this 1. Okay, so you're going to say left count 1, and here in the side greater than this 2, so only 4 and 3 2. Okay, so see here 2 is the output. Okay, so here see you are taking mid as 2 now. So here if you see, if you take mid as 2, so you have 0 to 4 and 0 to 3. Okay, these are the indexes, right? 0 to 4 and 0 2 3. Okay, so 0 2 4 if you take 4 1 and 2. Okay, and after that 0 2 3 you are taking 0 4 1 and 3. Okay, so see now 4 1 2 and 4 1 3. 4 1 2 4 1 3. Here also 4 1 2 4 1 3. Okay, both are possible. Okay, so this is actually what we are doing here. Okay, all right, so accessing tree 2, adding 1 to the sum, final query result is 1. Okay, updating index 2 with delta 1. Okay, so this you will get a better idea with the code, but here just understand what we are doing. Okay, so when you are at here, so smaller than this one elements just 1, greater than this one 2, so total is 2. Okay, so you already know when we are fixing this y, so what are those? Okay, then we are fixing y here. So now lesser than this 4 here, we have 3, greater than 4 here 0, so overall 3 into 0 is 0 only. Okay, and same way when you fix it here lesser than this, so you are going to get 1 2 3 only, and right count is 0, so total so far is 4, so final total good triplets is 4. Okay, so this is what you need to do. Okay, and these are some debug statements that I have added in my code. Okay, so we'll write code, okay, about this, how we are getting this bug statements. Okay, so let's move to the coding part. Okay, so what we need to do, right? Okay, now here first of all you have to use this Fenwick tree, right? So what you need to do here, do one thing, create one class Fenwick tree. Okay, class Fenwick tree. Okay, and here inside this private int tree. Okay, and then you have to constructor. Okay, use constructor to initialize the tree with the size plus 1, because this is one based indexing, right? So for that you have to write public Fenwick tree, and here int size. Okay, and here you have to write tree is equal to new int, and here size plus 1. All right, now here create one helper method to get the lowest set bit. Okay, lowest set bit we need, right? We were using that to reach to the parent. Okay, lowest set bit, so rightmost bit, that simply means. Okay, so here I can say low bit function. Okay, I will create that low bit. Okay, in this what we were doing, so if I'm passing this x, so we have to just return x, and we have to just do the and with minus x. That's what. Okay, this is going to give the low bit. Okay, done. Here I have shown you now. Here 3 minus 3, so lowest bit. Okay, so this is the lowest bit only, so this is what it is going to give. Okay, this is done. All right, now after that, once this is done, then after that what you need to do. Okay, so this is done. Now here there are update methods. Okay, to it adds the data to the given index and all of its parent node. Okay, so let's write the code for this. Public, okay, public void update, and here what you have to pass, you have to pass the index, int index, and int delta. Okay, and here we have to increment the index plus plus. Why? We have to convert it to one based indexing, right? So index plus plus. All right, now here you run one while loop. Okay, while this index is less than tree dot length. Okay, then in that case you have to just update the tree index. Okay, tree index, you have to add this data value. Okay, delta. All right, and now you have to update the indexes. Index plus equal to, this is the formula that I have shown you into for the update and arrange. Okay, so I have shown you that formula, right? So I'm writing that formula. Okay, index. So this is to move to the next affected node. Okay, because of this update. Okay, we are reaching to the next affected node. And then there is one query method which returns the prefix sum from index 0 to index. So I'm going to write that here. Public int query, and here int index. Then this is one, again one based indexing, so we have to increment the index. Okay, and then initially sum is equal to 0. All right, and then while index is greater than 0. Okay, here you have to update the sum as sum plus tree of index. Okay, and here again there is one formula, but instead of plus we have to use -1. Okay, so this formula I have already shown you. Okay, this is going to move to parent node. Okay, so here, see here now, this we are using minus here, index minus index, this one. Okay, this is simple formula that I'm writing here. Okay, so just go over this okay, all these details and try to understand the example. Okay, because it needs actually little bit efforts from your side as well. Because okay, I will try to make the video. Okay, in few days whenever I get a chance, I will try to make the video in detail about this. Okay, just add remind me in the comment section. Okay, whenever you see this video, and if you don't find that video in my channel. Okay, once I prepare the video, I will just attach that video in the description. Okay, once ready. But if I forgot, then just remind me. Okay, all right, this is done. Okay, now here query is done. Okay, and what is this query going to return? Here you can say it is going to return me the sum. Okay, so here in this part, this complete sum, I am writing here 7 2 5 in blue color. Okay, that is nothing but sum. This is what we need to update. Okay, in the affected range. Okay, now this is done. Now here this code we have to write. Okay, so here again int uh, n is equal to nums1 dot length. Okay, so length is going to be same for both. Okay, so we have to find the number of good triplets I, j, k such that I should be less than j, j should be less than k, and position of nums1 I, nums1 j, nums1 k in nums2 are in increasing order. Okay, so now here this is n value, then we have to map nums2 value to their position. Okay, so int posin nums2 is equal to new int n. Okay, and then run one loop for int I is equal to 0, I is less than n I plus plus. Okay, so here I'm talking about step 1, pose in nums2, and here you have to write nums2 of I is equal to I. All right, then after that you have to transform nums1 into a new array representing the positions of its values in nums2. Okay, int mapped positions is equal to new int n. Okay, and then again run this loop. Okay, now here what you need to write, map positions. Okay, mapped positions of I is equal to pose in nums2, and here inside this nums1 of I. Okay, that's it. Okay, so mapped positions of I is equal to position in nums2 nums1 of I. Now you have to just construct this Fenwick tree to count how many indices less than current position have occurred. Okay, so here Fenwick tree, and here Fenwick. Okay, new Fenwick tree, and here just pass n value. All right, then we have to count the triplets. Okay, long total triplets is equal to 0. All right, now again run one loop, int I is equal to 0, I is less than n I plus plus. Okay, inside this current pose is equal to mapped positions of I. All right, now we have to count of elements to the left that are less than current pose. Okay, so here int left is equal to Fenwick dot query, and here inside this just pass this current pose. Okay, this is done. Now we have to update the current position in Fenwick tree. Okay, so here what you need to do, Fenwick dot update. Okay, and whenever we encounter that particular value now, so we are just updating it with 1. Okay, so current pose and 1. Okay, and then we have to count to the count of elements to the right that are greater than the current pose. So here same thing, copy this. In the right side we have to calculate, so here we have to write int right. Okay, int right is equal to, here you have to write n minus 1 minus current pose. Okay, and here minus you have to write minus, and here you have to write I minus left. Okay, so left and right side you have to calculate, right? And then total triplets you have to just multiply. Okay, so here the total triplets is going to be plus equal to, okay, long left into right. Okay, done. Then in the end just return total triplets. Okay, so let's run the code and see if there are any code issues. So yes, there are some issues, so let's try to fix that. Here it should be index, right? Let's run it again. So there is one more issue here, current pose. Okay, so here what we are doing, n minus 1 minus current pose. Okay, so here this, so from where this is coming, current pose, here this. Okay, I'm writing it current pose, right? So let me paste this one as well. Okay, let's run it again. Okay, so now let's submit it. So see, our solution is accepted, right? So I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.